My name is Dr. Ma, and I'm very happy and pleased to welcome you all to the first set of presentations for a new course, G498, Technological Innovation Capstone Design. And what makes this course unique is that these students that you're going to see today, they identified, came up with, and developed the problem that they have solved and have been working on their own. So they went out into the community or identified something that they wanted to work on, and they developed and defined that problem, and then worked on developing a solution to it. And you'll see how far they've gotten and what they've achieved today. You're going to see 4 presentations if you stick around for all of them. There is 2 group presentations, and then there's 2 individual presentations. So we're going to be starting off with Design U. And then after Design U will be their mechanical engineering student doing his own shorter presentation on that specific subsystem. Likewise, Vertical Connection will do the next group presentation. And then their mechanical engineering student, Devin Bradburn, will be doing a short presentation on his specific work on mechanical engineering, because they are actually in 2 different courses. There's the broad group course, which was a full year course, and then the mechanical engineers, Stefan Belev and Devin Bradburn, were each doing a 1 course credit to assist these groups, and they certainly contributed in a major way, as you're going to see. So the group presentations will be 15 minutes each. The individual mechanical engineering presentations will be 10 minutes afterwards. During the question and answer period for the larger groups, we'll have lots of time for everybody to ask questions. If there are mechanically oriented questions, we may defer some of them until after the mechanical presentation, because the mechanical engineering students will go into more details on the mechanical subsystems. But if there's something you really urgently need to know, don't hesitate to ask, and I'm sure they'll be able to answer just fine. We have food and drink at the back if anybody wants to grab some as the proceedings go along. We'll take short breaks between the presentations, but we should be here for about an hour and 10 minutes overall. Any questions before we get going? I'd also like to recognize that we have a few guests here today from the community, from the Saskatchewan Abilities Council. We also have some guest judges and evaluators, Dr. John Moffat from the School of Professional Development, and from Electrical Engineering we have Dr. Andin and Dr. Denard Lynch. So we're really happy that they've been able to come out and join us. So without any further ado, I think I will turn it over to Design U, and they can get going shortly.
Thanks so much, Sean. And thank you, everyone, for coming out, too. This is great to have so many people coming out. Great. All right, so my name is Surath Gomis. I'm an engineering physics student. This is Dallas and Thomas of electrical engineering, and Stefan of mechanical engineering. And like Sean said, we are Design U. And we are 4th-year engineering students. This is our final design project, and we have isolated a problem in the research field of upper limb prosthetics. All right, so just to kind of go into prosthetics a bit. So really, when we consider grip is something that we all kind of take for granted a lot of the time. But when it comes to prosthetics research, it's a very important function that has to be considered because it's so fine detailed, there's so many intricacies to it, and to make the overall best prosthesis to be used by an upper limb person with amputation, there's a lot of things to work out, right? So when we consider the conventional hook prosthesis, this is the actual prosthesis that users generally use. See it depicted here. I'll just kind of go into a bit of how it's operated. So for one, the user will have the hook attached to the socket, attached to a cable assembly on the back. And as their user pushes their arm forward, this tensions the cable that's attached to their back, and this causes the hook to open. As they release that tension on the cable and bring the hook backwards, the hook closes with the force of the rubber bands that are kind of near the end of the hook, as you see right there. All right, so I've already established that this is the commonly used prosthesis, right? But we still think there's merit in actually increasing the functionality of it, because there are still a few limitations in it, right? For one, there's a limited functionality in terms of controlling the closure of the hook, because you can't control it to differently sized and weighted objects that easily. Secondly, there isn't very much direct feedback that's given to the user in terms of how well they're holding onto an object, whether it be something that's light, something that's heavy, etc. Right? Because all it is that static force from the rubber bands put onto the object. So these are things that we kind of want to explore and solve. Ultimately, with prosthetics, the ultimate goal will be to make a prosthesis which can be used as comfortably as one's existing arm. So this is the broad, overarching goal that we want to see, but we're making small strides towards this, and that's what we're going to talk about now.
All right, so to first look at like how you'd want to actually improve the hook, we needed to take a look at how the regular steps to grip that most people use. And traditionally, when you go to grab an object, you're going to need to understand as much as you can about that object. Most of us use visual stimulus or tactile feels like sensation, and we just need to understand as much as we can. And once you have this grip on an object, you also need to know kind of when you have applied a sufficient amount so you don't apply too much and damage an object, because we don't want to do that as well. Once you have this sufficient grip, you're going to pick it up, but then you need to kind of respond to other factors in the environment, like slippage or change in texture or any other reactionary things that may happen. And so these steps considered, and due to the limited functionality and the limited direct feedback, as Surath mentioned, we then proceeded with the following problem statement. Persons with a below elbow single arm amputation who use a cable-driven hook prosthesis have a limited ability to pick up objects of different geometries and weights without damaging them due to limited perception and control of their hook's grip strength.
All right, so now that we have a good idea of what the problem background is and our problem statements, the rest of this presentation will focus on the steps we took to arrive at the proof of concept we have today. This entails going over the functions and objectives we had for proof of concept, as well as the design process involved, which involves making alternatives and selecting a final alternative. And this goes over the mechanical subsystem, which Stefan will go over, and the electrical subsystem, which Surath, Das, and I will do. Finally, we would go over the future work that we would like to do to see this project to completion and see a successful project in the end.
Great, so we'll just get straight into the functions and objectives of our project. So these functions and objectives demonstrated or depicted here are for proofs of concept. So there's two main functions, and these relate directly to the mechanical subsystem that Stefan will be talking about briefly in our presentation and elaborate in his presentation, and also another function which we directly were trying to solve with our electrical subsystem. For the first one, we wanted to demonstrate the function of a controlled hook closure. So this is to actually increase the ability for the hook to grab objects of different sizes and weights and apply different forces to them depending on that object. Secondly, with more so our subsystem, with the electrical subsystem, we want to demonstrate the function of providing grip perception to the user. So what this entails is giving the user a bit of sensation into how well they're holding onto an object and the quality of that grip, whether it be something that's held that's light or soft, or something that's held that's heavy or differently sized. With these functions in mind, we had a few objectives that we want to complete. So we want to grab objects of different sizes and different weights, but we also want to create a solution which is still intuitive for the user to use and has limited extra fatigue when they're using it.
All right, so with a proof of concept in mind, we needed to first tackle how we were going to get to this proof of concept. And ultimately, it was a very complex system and complex problem, so we needed to break it down into two subproblems, as Surath alluded to. We have provide the grip perception, which was that understanding that he's talking about, and also control the hook closure, just so, because it's so limited in the ways that it actually closes, we want to broaden that reach that it can actually close to. And so the electrical subsystem of providing grip perception is something Thomas, Surath, and I tackled, and then the mechanical subsystem, due to the nature of the 498 class, we were able to have this interdisciplinary connection, so we enlisted Stefan Belev to do the mechanical. And ultimately what would happen we would kind of have this control signal that would say maybe close the hook more, close the hook, stop closing the hook. It's going to be a simple signal that he can then use to implement his function and actually carry that to completion.
I don't want to take up too much of their time. I have my own presentation to do, so I also don't want to give away too much. Do you mind if I just borrow that for a second? But this is what the mechanical design looks like. So as you can see, it uses a gear train over here that's attached to the hook. And what that gear train does is it amplifies any movement on the hook end by a large amount, such that we can actually lock the hook in many, many discrete increments via a ratchet mechanism, which is kind of hard to see with the glare here. In addition, this ratchet mechanism is controlled by a linear solenoid actuator. And what that does basically is it can push or pull based on an electrical control signal. So what this system does is as soon as it gets a signal from these guys' control system telling it, hey, you need to stop the hook now, it rams those pawls into the ratchet mechanism, locks the hook into place, and holds whatever object you're trying to hold. That's the gist of it. Let's get back to the electrical guys.
All right, so clearly Stefan has shown that there's a solution. But no, he'll actually show the solution during his demonstration. But to get this signal to him, we needed to brainstorm how we were going to do that. How are we going to give this perception of grip and how well someone is actually gripping an object and give it to Stefan's system? So our first basic alternatives that we had were auditory stimulation, visual stimulation, and vibrational stimulation. And ways of implementing this we also discussed were visually, you could have something as simple as a light that would maybe trigger when enough grip has been placed, or a variation of lights that could go off with a variation in grip. Also, visual stimulation, very similar, could have been implemented with a beeping sound or another recognizable auditory sound. And then vibrational stimulation could be implemented with some sort of vibration that simulates the receptors of the fingers, kind of gives a sensation to the user of in another area of their body not directly associated with the hook. And that varies with the hook. So ultimately, our choice of alternative was this tactile vibrational stimulation. And this was largely due to the fact of these sensors or these vibrational motors can be very small. They don't protrude very much. And also, research done by the University of Zurich, as Thomas had found, proved that these vibrational sensations could be easily learned. And this was a big aspect to our choice.
Great. So I think we're actually ready now to actually demonstrate our proof of concept. Actually, let's keep that hidden for a second. I'll just describe it first, and then we can kind of do that demonstration. So ultimately, with our proof of concept for our electrical subsystem, which is supposed to demonstrate the function of providing a grip perception to the user. Ultimately, what the system is a haptic feedback system. So you can envision it like this. If you have some type of force sensors on the ends of the hook, as the hook is going to go around an object, the sensor readings will change. These will be correlated to the vibrational motors that we actually have on a cuff right now, which will be put on the upper arm, on the other existing arm, or somewhere else. And then as you increase the force of your hold on an object, the vibrations will increase in intensity and speed, and you can kind of get that sense of haptic feedback for how well you're holding onto an object. So fundamentally, it all goes down to this. So this is the force-sensitive resistor that we use. Essentially what it does, it can correlate forces with changes in resistance through it. So this is more of an electrical side of things and a bit more specific, but as you press down on the sensor, its resistance changes. And so through our circuitry and then through our microcontroller, brains of the machine essentially, these can be correlated to the cuff that we have right here. So we'll show it to you again. But as you increase the force of the sensors, or on the sensors, because the hook is picking up an object, these motors will vibrate in greater intensity and greater speed as they pulse alternatively. So we're actually going to demonstrate this right now. So let's bring it up. Maybe here? Great.
Grab the bottle for me. So as Surath puts on his sleeve, I will describe this here. What I have are two of the force sensors on the tips of my fingers to emulate the two contact points of the hook. And can you pass that over? Thank you.
All right. Great. So as Thomas here is going to be, mimicking how the hook will operate, he's going to start applying force to the object, and I'll start to have that kind of feedback. And so you can hear it right now. So Thomas is going to slowly increase the force on the object. So the intensity of the vibrations and also the pulsation frequency is increasing. So to a point, I will say, okay, now I have sufficient force and grip on this object because I've kind of correlated these vibrations with my sense of how well I'm holding on an object. And then at some point, I can say, oh, okay, I can pick up the object. At this point, it's still up to debate, but we could take this as a control signal to send to Stefan's system automatically to close or to actuate the stopping mechanism of his hook so that it could stop at its discrete position, or perhaps it can be the user who actually just presses a button on the prosthesis or something. This is still up to the debate, and we still need to talk to a lot more people to see what the best solution is. And so one thing that's also important to consider as I take this off is that what we've done here in demonstrating haptic feedback was specific to what we as a group thought was appropriate for a sensation, right? Because what we've done here is we have a cuff, we have vibrations that increase in speed and intensity, and we felt this was the best type of haptic feedback, but ultimately it's up to the user, right? And the beauty of our system is that it's very changeable. Essentially, these vibrations are through the software, which we can change according to the user's needs. So as we talk to actual individuals who will be using the system, we can change the vibrational frequency or different pulsation patterns, etc., depending on what the user feels is the best way they can feel that haptic feedback, the best way they can get information of how well they're holding onto an object. So there's still a lot of modularity in the system, and that's what makes it a good design and concept, we think. So ultimately what we've done here is that we've demonstrated our two functions. So first with Stefan's mechanical system of controlling the hook's closure, which he'll describe later in more detail, but also providing that grip perception to the user so they have a sensation of how well they're holding onto an object. So our initial problem has been solved to that extent because we've actually explored these options and solutions for them. But now let's anticipate some further work and further problems.
So to anticipate any further work we have to do, let me refer back to the diagram we had at the beginning. We have these two subsystems that, on our side, the electrical side, we solve the problem of grip perception and be able to perceive the grip quality on an object. And whereas Stefan, he has solved the problem of controlling how the hook is closed. So the next immediate step is to build both proofs of concept and integrate the two and work out any kinks we may have in integrating the systems. And then we would like to consult with users and get their feedback from it and get information that we would like to use to modify our system to improve it, what's bad about it, what's good about it, and continually improve it based on how flexible our system has been so far. Then we'd like to anticipate any future problems with an electrical system. To do that, we go back to how an object is handled. First, you have to perceive the grip. Then, once an appropriate pressure is applied, you pick up the object, and then you must react to any changes in grip quality. And to demonstrate that, I have a video. In this video, I am picking up an object, setting it down gently, and I'm picking it up and letting it slip. So it's data like this. On the top plot there, they're just raw force readings. And it's data like this where we can begin tackling the very difficult problem of identifying slip and grip quality and what makes a good grip. As you can see, details such as the slope of the reading as the sensor, or as the object is being put down. It's longer. The duration of the force sensor reading going down is longer compared to the slip sensors, right? The slope is very steep. And using analysis such as a discrete time derivative, which is basically just tells us what the change in the sensor readings are at the time. Using information like this, we can help identify what slip is and how we can characterize it and be able to adapt to slip.
Okay, so to reiterate, grip is something that most of us take for granted, and we all use our hands in our day-to-day basis or on our day-to-day lives, and we don't really think about it. We grab door handles, we grab our phones, we grab everything, and we don't really think about it. But to actually lose this privilege would be an extreme detriment, and most of us would gravitate towards using these cable-driven hooks because they're so common. So although they're cheap, we feel that there could be a more well-rounded solution, and our proof of concept here, as Stefan will show his in the not too distant future, we've made strides to actually show that stimulation can be felt and it can be varied depending on the grip that's applied. And so we've kind of tackled this perception of grip, and we've also made strides in the future towards tackling characteristics of slip and future work. So the work we've done has been promising, and we're optimistic about the future. So thank you very much. And any questions?
So we have time for several questions.
All right, you want to start? I have a quick question. When you did your demo there, I think Surath put that sleeve on.
Right.
You had it on your left arm. I noticed that Thomas was picking it up with his right arm. Do you have any targeted arm for the feedback band?
So ultimately, the goal of this is for a single arm person with amputation. So as of now, how we kind of envision it is that perhaps the sleeve could be put on the upper arm of where they're using their hook. But of course, like we've talked about, this can be changed according to the user's preference.
I presume the users are the amputees. Who are the clients for your product?
All right, Tom, we'll talk about. I can talk about.
Well, so yeah, of course, the users, as you described, are the persons with amputation. Clients, there's a myriad of them, right? They could be people such as Dwayne from Saskatchewan Abilities Council. So I'll introduce them. Dwayne is a prosthetist here at the Saskatchewan Abilities Council, and what he does is he does all the fitting, and they get all the prostheses that are used, including myoelectric prosthetics. So not just hook-driven or cable-driven hook prosthetics, but also these more advanced ones that use motors and are electrically driven. So Dwayne is a potential client, and of course, just certain other manufacturers of prostheses. So there's Autobach is one of the leading manufacturers of cable-driven hook prostheses. So if we get to a point where we see that implementing this in a hook prosthesis does have sufficient value, and it could be made further than a proof of concept, further than a prototype into actual production, that's of course someone else that we can contact as a client.
Did you come across anything in your research, like how long it might take for a person to adapt to that vibrational feedback and to turn that vibrational feedback into like an instant response or an automatic response?
Right.
You mentioned I think you can learn it quite quickly.
Yeah. So to back that up, research done by the University of Zurich back in 2012, so fairly recent, we found that it was a research paper on detecting slip, and it was a very basic apparatus setup. What it was a prosthetic arm. It was positioned in such a way that there was a block fitted within that arm, and then according to some signal by the invigilator, the block would slip, and then the person controlling the prosthetic arm would have to react to it. And they did 2 different trials that were important to us. One is a visual trial where the user would detect visually the slip and respond to that. And then the second trial was a vibrational reaction to it. So when the block started to slip, they would feel a vibration, and then they would react to that vibration rather than the visual stimulus. And it was found that visual stimulus initially, was the fastest. They reacted to the block the quickest. But with vibrational, only after a few runs, trial runs with vibrational, they found that the vibrational actually caught up. The reaction time of the vibrational came to par with the visual stimulus. So as something as intuitive as seeing something slip, the vibrational can be trained to be as intuitive as seeing an object slip from your hand.
I think it was a good choice to use vibrational because a lot of times we don't want to bother looking at the objects we're picking up.
Or you're unable.
Or listening, yeah, depending if it's dark or loud or, yeah.
Is there any concern that the vibration could get ignored just because it's this like constant? For example, if you're moving something from one pallet to another, that constant vibration that you just kind of get used to, that you kind of then take for granted. Fair enough.
So initially with our system, we didn't demonstrate exactly how it happened once you have the object held up, right? So the vibration just continued as long as you're holding it. But further implementation would be something like you pick up the object, you feel that vibration increasing, and once you actually you send the signal to lock the prosthesis, the vibrations would stop. So the vibrations are initially for actually picking up the object and exerting the correct amount of force, because that's directly correlated with Stefan's mechanical system, which closes to discrete positions. So once you close to the the proper discrete position, depending on how much force you're putting on it, and you can feel that force with the haptic feedback, then the haptic feedback would stop at that point. But then, of course, we try to implement the slip, and that could be additional buzzing to say, hey, something's about the slip, or it could be controlled automatically. If you want to talk about that.
And then just to add to that, like it goes to our the modability of our system, in that we can change how it's controlled, and we can adjust it to the user's preference, whatever they'd like, right? So maybe the user would like it to actually always be constantly going. We can have that done fairly easily and fairly quickly too. And that's just, that's one strong thing about our design thus far.
Question over there.
Just curious, you guys have looked into the issues around pedicle strain injury with current hook prosthetic systems, and how your system may be able to address some of those concerns?
Could you repeat that?
With current hook prosthetics,
Yeah.
hook and cable, there is issues around repetitive strain injury. I
Right.
just wondering if you guys have looked at that at all with your system.
Yeah.
So like when back at the beginning when we were trying to define our problem and what the issues we would like to solve, that was an issue that came up in like strain on the user as well as strain on the cables in actuating these hook prostheses. It was a serious concern, but it was a concern that we didn't think we could quite tackle in the time frame we had, so we went with a not to say simpler, but an objective that we think we could accomplish better within this time period.
I see Surath slipped over during the last question and popped the battery out of the battery case there. My question is a little more technical. What steps are you going to take to make this a reasonable size and to turn this thing on and off to make it sort of energy efficient?
Right.
All right, so ultimately right now it's running off, Stefan will elaborate as well, but his mechanism I think runs on 12 volts. Is that correct? So ideally that's the kind of restraint that we have, and I think he may discuss more of that in his actual presentation of how that's going to be implemented. But we don't need two sets of power. It will just be the power for the mechanical system and for the electrical system. So ideally our electrical system will use pretty much whatever his does, because it's going to be able to take that electricity and use and power our small vibrational motors and the micros. So as for how we're going to get it down to a smaller size, there's a lot to simplify and how to get it smaller. So I mean, you can maybe elaborate if you have an idea, but I mean, that's way further down the road.
Yeah, this is nothing that we've necessarily discussed as a team yet, but we still have a few alternatives we can kind of look into. Just in the sense of a 12-volt battery or something like that. Well, quadcopters, these hobbyist quadcopters do have higher voltages, and these batteries are roughly yay big. So that could be something we could try to implement. Already, myoelectric prosthetics do have voltage sources in the form of different batteries. So those are made really small and thin as well. So we can explore those options. But yeah, ultimately, we have to scale it down, right? Like that's something we have to look into further. And once we do the scaling down, then we have to look into more of the concerns about safety of the batteries and how we're going to encase them, just in case there's a chemical spill, or if the battery to break, or some other kind of rupture. So those are further considerations. At this point, since we're just doing a proof of concept, those weren't necessarily the main objectives. But of course, those are very important to consider in the future.
If I could follow up quickly, on the first part might have missed my point. It was sort of energy efficiency. I realize maybe you haven't done it at this point.
Right.
Have you thought about ways to kind of wake it up from sleep so you never have to take the batteries out? I'm assuming that Stefan will tell us that
Stefan has something.
he's going to say something like, it
Go ahead
doesn't take
right
any
now.
power to hold, it just takes power to break
No,
it.
exactly that.
Yeah.
You might as well take the mic from me, Denard, because that's exactly what I was going to say. So the only electrical component that the mechanical subsystem uses is that electrical solenoid. And while it is 12 volts, it's specifically designed for intermittent use, and to engage the pawls and lock the hook, that actually uses strictly mechanical power. So the only time you're using electrical power is when you're going to open the hook, which is a pretty short time period. So over those couple seconds, you'd have to run power to the solenoid, but the rest of the time it's a tensile return spring that holds it into place. And I mean, compared to that 12 volts, and it's also 12 watts, I believe. There's also room to downscale, but that's a whole nother story. But that's definitely the biggest power drain, and it's very intermittent. So in terms of running things energy efficiently on the mechanical side, I think we've got that figured out, and then there's room to be smart with the haptic feedback.
Cool. Thank you.
Okay, well, I think if there's no other questions, thank you very much, Design U. So Stefan Belev is a mechanical engineer, fourth year mechanical engineer, a key part of the Design U team, but he was acting in a subcontractor capacity with the Design U group, made up of EP and electrical students, and he was working on the mechanical subsystem. This was a one course credit, although as you'll see, he certainly outdid himself on this. So take it away, Stefan, you've got 10 minutes.
So the biggest challenge in this project is actually living up to that introduction. So what I did is I designed a locking mechanism for this prosthetic, and that locking mechanism was specifically designed to enable the type of haptic feedback and control that these guys who technically contracted me wanted. So what are we going to talk about today? First of all, the problem definition. Now these guys did a wonderful job of explaining, why we tackled the project in the first place, but what I want to specifically explain is the problem from a mechanical perspective. What are the issues that I needed to solve specifically? Next, I want to take you a little bit through the alternatives that I considered in my design and what I ultimately ended up choosing. Finally, and this is probably the funnest part here, is going through the proof of concept, looking at some cool SolidWorks animations and figuring out how the whole thing works. And then we'll wrap up with what I have to do to complete the project, so future work, and then I'll take any and all questions. So first things first, what was the problem here? Well, as we kind of covered, this is what the prosthetics look like. And they use these really heavy-duty rubber bands to apply force on any object that they clamp around. But the biggest problem here from a mechanical perspective is that these rubber bands, they're very heavy-duty, act exactly like a spring. And the way a spring works is it applies as much force as how stretched it is. And this is a really big problem because in the case of prosthetic users, now all of a sudden you can't control how much force you're putting on an object. The amount of force you're exerting on that object is completely dependent on how much the hook has to pivot and stretch to close around it. So a really big object like a wine glass would actually have a bunch of force exerted onto it because it's trying to hold the hook wide open. And this is obviously a problem because, as we know, if you grip a wine glass or a crystal glass too hard, boom, it shatters, it's gone. So the issue here is right now you have a static grip, which means you basically get some force exerted on the object depending on how big it is, and you can't control that force. Not very handy for picking up a wide variety of objects. So this is the exact same problem statement. Let's condense it down a little bit for the mechanical guy. So essentially the problem here is I have to pick up a wide variety of objects. I can't break those objects. They can be different weights, sizes, shapes, materials. I have to hold all of those objects. I can't drop those objects. I can't break those objects. Pretty simple, actually quite complicated to achieve. All the functions that I have to do. So first of all, I have to mount onto the existing prosthetic. Whatever I come up with, it has to attach somehow. It has to interface with the prosthetic somehow. In general terms, I have to increase, decrease, or maintain some amount of grip strength at the end of the hook in order to hold an object properly, not break the object, not allow the object to slip. And then finally, I have to have some means to allow the user to cancel the grip at any time, just in case my system screws up or they decide they don't want to hold that object anymore. Basically, there has to be an abort button or something of the like. In terms of objectives, there were a lot. So let's just go through them really quickly. What adaptability means is I wanted to create a design that works across a bunch of different types of voluntary open prosthetics. So I wanted to create something that doesn't just work for this specific prosthesis, but actually works for a wide variety of hook prostheses. I wanted to keep the cost down for obvious reasons, right? Like I'm not trying to make money off this. I'm trying to help people. The cheaper the better in that case. In terms of weight, this is actually very important for prosthesis users because, put yourself in their shoes, right? Whatever you have is on the end of your arm or whatever for pretty much the whole day. So if it's cumbersome, if it's heavy, it's not easy to use, it's not pleasant to use. So if you keep the weight down, the lower the weight, the better. In terms of aesthetics, we all like to have things that look nice, so I didn't want it to be cumbersome or clunky or anything like that. I want it to be sleek, I want it to be something you could be proud of owning. In terms of reliability, this is something that you would potentially be using to hold fragile objects, to hold somebody you care about. So in those cases, I don't want to crush or hurt those things. So 99.997% of the time, I want this thing to work. The more reliable, the better. In terms of versatility, the world is full of a bunch of different objects in terms of sizes, shapes, weights, textures. I want it to be versatile and able to adapt across all those objects and pick up those objects well. In terms of durability, this is especially important in Saskatchewan. So we have corrosive conditions, extreme temperatures, moisture, no moisture, basically a bunch of conditions that break things. I want my design to resist all those conditions and be durable. Finally, speed. I want this to operate as fast as possible. One of the things that prosthesis users like about this is that it's very simple, right? You open it, it closes itself, you move on. It doesn't take, it doesn't take you 5 minutes fumbling with a myoelectric or something like that to fine tune, the control and grip on the hook. It's open, close, move on with your life. So the faster it works, the better. Finally, the constraints. So the main constraint is that prostheses users actually love these a lot right now. They're very common, they're very robust, they're very reliable. So I wanted to maintain all the original capabilities of the prostheses, such that if you don't want to use my system or you want to remove my system for a period of time, that your prosthesis would function just like it did before. The other constraints were essentially mostly financial constraints, meeting the health and safety standards, and just being faster and better than the traditional method of adjustment, which is essentially adding or removing elastic bands. So with all that said, let's get into some alternatives. These are basically design options I considered. So alternative one was looking at using a torsional spring and dynamically adjusting the spring preload. So what you would do with this alternative is you'd basically remove the rubber bands altogether, and you would use one of these guys. This is a torsional spring, and it basically works like a normal spring, except instead of stretching it or compressing it axially, you just twist it back and forth. So the idea here is you'd put this on the pivot point of the hook, and then you'd use a motor or some other kind of mechanism to adjust how twisted it is to begin with. And if you could adjust that on the fly, you could actually adjust how much force that spring is exerting on the hook end. Where you may have seen this is actually on your garage doors. So garage doors have these big torsional springs on the top, which are actually preloaded to offset the weight of the garage door, such that a motor the size of that projector can move your door back and forth. So similar principle, but used on a prosthetic. Alternative two was the idea of using a linear actuator. You could use electric, hydraulic, or pneumatic actuators, but basically they're just these piston cylinder type of mechanisms which allow you to push something forward or backward along an axis. So the idea here was you mount one of those on the claw and you use the force of the actuator to control the strength at the tip. Alternative three was actually keeping the elastic bands and designing some kind of locking mechanism which stops the hook at a discrete point. This is the one I ended up choosing. I kind of spoiled that in the first presentation, so no drama, unfortunately. And finally, the last alternative was kind of using the idea of a tabletop vice grip and a motor. So as we know, the vice grip, the more you crank it, the more it squeezes something. So the idea behind the prosthetic is set it up like a vice grip, put a motor on there, and then tell it how strong it needs to grip the object. So my selection process, I looked at all my objectives, I decided which ones were most important, and then I applied each of those objectives against each design to design alternative to decide how well that alternative met those objectives. And what I ended up picking, like I've already said, is that locking mechanism. So here's the fun part, the proof of concept. So even though my thing is a mechanical subsystem, it also has subsystems, and those are all the subsystems. So first one is how you actually achieve the locking. So what you're seeing here is a staggered ratchet gear. So the way a ratchet gear works is you have the ratchet gear and you have the pawl mechanism. And in one direction, these wheels are free to rotate, but the moment you try and rotate in the other directions, it gets forced up against those pawls and it basically locks the mechanism. So by staggering two ratchet gears together, I'm basically allowing this mechanism to lock in increments of 5 degrees. One important thing to note is that because there's a solenoid actuator holding these up in the overrunning position, they don't actually bounce up and down during normal operation. And that's important for controlling noise. The other part of the locking mechanism is that push-pull solenoid that we were talking about. So actually this one only pushes up to remove the pawls from the ratchet gear. And because it has a tensile return spring, that spring automatically brings the pin back down when the control system tells it, let the pin go, you need to lock the mechanism. So these are the specifications of the linear actuator. And I've been doing some research, and there's actually significant room to downsize this both in terms of power requirements and in terms of space requirements. So the gear train, while we have a locking mechanism, its resolution on its own is actually not high enough to grasp a wide variety of objects. So what I did is I mounted it on an 85:1 gear train, which amplifies any motion at the hook end towards the ratchet. So you'll notice in the animation, even though we're not moving very fast at the hook end here, that this ratchet is just given her, really. And that's because of that 85:1 gear ratio. So by using that amplification mechanism, in each locking increment, you get that angular displacement and about 1/10 of a millimeter. So you basically have really, really fine control in terms of how many positions you can lock the hook in. Finally, in terms of mounting components, how does this attach? Well, I'm going to pass the hook around right now. And as you can see, once it gets to you, this prosthesis actually threads into a socket. So there's an extender piece which has the same type of thread on one side and then a female socket on the other side, and it basically just extends that threaded connection. And then on that extended piece, you'll also see a slot. So the whole gearbox and housing basically just slide in, and it isn't pictured, but there would be a pin or a bolt that holds it into place. So the important part here is it's really easy to install and really easy to remove, so it meets those criteria and objectives. Finally, one thing that isn't pictured but I would love to have in my proof of concept is elastomer sleeves, which is just a fancy way of saying I want like a soft rubbery material on the tines of my hook. And this is important for two reasons. First of all, it's kind of like a soft material, so it provides mechanical cushioning. It's easier to hold more fragile objects. But it's also important in terms of detecting slip, because something rubbery is kind of sticky against objects. So one, it holds the objects better, but when they start to slip, you get a kind of stick-slip means of slipping, which is much easier to detect. So those are two reasons why I would want those sleeves on the prosthetic. So I'm going to play you guys a video of this thing being assembled. Or deassembled, I guess. Unassembled. And this is just to give you an idea of where everything goes and just how compact it is. So while we're watching this, I know this thing can look big in comparison to the prosthesis, but that box just across that width there, that's 5 centimeters. So it's actually not very big at all, which is important. This is a render of the final design. This is kind of what it would look like once it's built out of the materials I've specified. This is it from the backside. And finally, let's talk a little bit about future work. What would I need to do to get this thing to market or get this thing usable by people? So first of all, I'm still in the process of doing technical analyses. I'm going to do a bunch of stress and deflection analysis, make sure nothing's going to break or bend out of place or that kind of thing. I'm going to look at the wear and fatigue life and determine how long the solution would last, how long you could rely on it for. I'm going to look at the thermal effects, which is especially important in Saskatchewan. We see very large swings in temperature. And finally, I want to build the physical concept, see that it's actually responding as fast as I've predicted, see that the resolution is as fine as I've predicted, and finally determine the need if we need to be slowing the hook down via mechanical dampening such that we can get a better signal. So a bunch of physical tests that you really need in order to get anything into market. So with all that, we've talked about all the parts of the mechanical subsystem, and I'll accept any questions.
I guess I'll start. Awesome, Stefan.
Thank
Like
you.
very, very cool. Your alternatives, some of them were kind of self-powered and some of them were still, sort of cable-powered. And it seems almost like apples and oranges. How did you compare those two different things?
So it's interesting that you would say that. The way I compared them is not so much against each other because, like you said, they're apples to oranges. But I compared them against different types of existing prostheses. So, for example, the next level up of prosthetic would be a myoelectric, which kind of uses motors and other types of actuators to achieve control and grip. So I compared what functionality I would be giving this prosthesis versus a comparable myoelectric. In order to gauge its performance and how much value I'm adding. Because it is easier to compare it that way than to compare it to a almost entirely different mechanism. Yeah.
Do you have an estimated weight of that unit?
I'm glad you asked. So SolidWorks, the program I drew this in, is very handy because once you've described the material, it can figure out how much everything would weigh. And including the weight of the hook itself, this would weigh less than 1.5 pounds.
Including the hook?
Yeah. So I believe just the parts I'm adding are clock in around 0.7 pounds, something like that. Maybe a bit less. I have the numbers in my logbook if you need an exact figure.
I noticed you had a spring loaded solenoid there, which you mentioned, and it sort of works one way. What I didn't catch on there was which way you fail-safed it. Did it fail-safe on locked or locked?
It fail-safes locked. So basically, in order to disengage the pulse from the system, you have to be using power to work against the tension spring. So if you ever lose power or something goes wrong, such that the solenoid depowers, that spring will force the pulse down and lock the mechanism in place. So if you ever lose power unexpectedly or something like that, the idea is the thing stops before crushing, or before dropping something.
So if you were crushing something by mistake, how would you solve that
So this is the beauty of the ratchet mechanism, because even if you haven't told those paws to disengage yet, if the user decides, oh no, something's going wrong, they can stretch out their arm just like they would normally. That ratchet will overrun, it will release the grip. So if at any point you decide, oh, something's going wrong, you just use the prosthesis as you would normally.
Follow-up, if I can. You mentioned that the mechanism was light, but I'm wondering how much mechanical inertia you're adding to the hook opening and closing by having the gears attached.
So right now, the inertia or resistance you'd be adding would just be the frictional torque you see from the gear train kind of meshing incorrectly or against the axles. And that's honestly really hard to predict analytically. So that's one of the things I would want to analyze with the proof of concept. I would measure I'd throw an elastic band or 2 elastic bands on the prosthesis without my system and with my system and measure the change in response times. But that is important from a performance perspective. But one thing I will add is that the inertia or resistance is not necessarily a bad thing, because if you force the hook to close slower, it gives you more time to get more sensor readings and a more accurate response. So damping the system is in that way maybe negative in terms of speed, but it might be positive in terms of accuracy because it gives your sensors more time to get readings.
All right, I think we'll let you off the proverbial hook.